last time we talked about using separation of variables to solve the heat equation. And because this is so important and fundamental, and because, that's what this class is all about, I would like to just go through the procedure once again very quickly. Just, the more times we can see this procedure, the better it'll be for us in terms of absorbing the material and understanding what's going on. Also, there's a lot of moving parts to this, so it definitely warrants looking at it carefully. So first of all, I'd go back to looking at the original problem. It requires some amount of mathematical knowledge just to understand the formulation of a PDE. Okay, so here we have the actual model, which explains how U is behaving inside the domain. And then we have this boundary condition, which explains, tells us what U is doing on the physical boundary at the left and right end of the rod. And then we have this initial condition, which tells us what U is doing on the temporal boundary, the time boundary, when t equals 0. So, of course, now the game is to try and find a function U that satisfies all three equations. Also, the analytic part is important, that it'd be differentiable and all that kind of stuff. So I mentioned this before. And so, typically, and we'll look at an example of this today, but typically, I would assume our solution, U of xt, the temperature, is made up of a steady state solution that's not dependent on time, plus what we call a transient solution that is dependent on time. And so I'll talk about this a little more today. In this particular case, we don't do this because in this particular case, because of the boundary conditions, the steady state solution happens to be trivial. And, I'll come back to all of these points shortly. So just, be patient with me here. Like I said, there's a lot of moving parts and there's a lot of little stories to tell you about what's going on. So here, in this case, because the steady state solution is trivial, we can apply separation of variables directly to U of xt. If the steady state solution were not trivial, then instead we would apply separation of variables to V of xt. Okay, and I will talk about that today. Okay, so what does that mean, applying separation of variables? Well, it's basically assuming that our solution the variables can be separated, that I can write it as a function of x only times a function of t only, and that, this is a non-trivial solution. And so now the math starts. It's really important that you appreciate, okay, what do we do with this assumption now? So we take this assumption and stick it into the heat equation. And this is pretty much the only part, where the heat equation makes an appearance. After this, once we decouple the problem, we're doing ODEs. And so here, by substituting, we're able to separate the variables. And then on the left-hand side, you have a function of time. On the right-hand side, I have a function of x, the spatial variable. And so we can prove analytically, but we can also kind of reason that the only way this variable of t can equal this variable, this function of x, this function of t can equal a function of x, is if they're both equal to a constant. So here we set them both equal to a constant that we're calling negative lambda. Why the negative? It's just convenient mathematically. It'll fit our intuition later. And so now we end up getting two new sub-problems. One's called the time domain problem. And so, that's from setting the left-hand side of the equation here to negative lambda and solving. And then we have what's called the boundary value problem, or the x variable problem, or the eigenvalue problem, which is in the x variable right here. So this would be called the boundary value problem. So one's sometimes called the t variable problem, and the other is called the x variable problem, or the time domain problem, and the eigenvalue problem, or I guess space domain. So now we want to solve these. And so we use the ODE technique of separation of variables to solve the time domain problem. That's kind of the easy part, like solving this ODE, that's the easy part. And there's not too much vector space theory involved. So here we're able to separate variables, integrate both sides, get G of t as, this exponential term. Now we use the boundary conditions. Okay, so this part's really subtle. Like, it's really important now that you appreciate, oh, this is where the boundary conditions come in. And so the boundary conditions on U allow me to find boundary conditions for F, right? So the boundary conditions on U get translated to boundary conditions, on F, on the F function. And so now here's our eigenvalue problem, or the boundary value problem, that involves the ODE with the boundary conditions. So here's a place I want to let's just stop for a second. So here, think about how this problem might change if the boundary conditions were different. In this case, first of all, having this equal 0 is a big deal. Having it equal 0 is one of the reasons we get a trivial solution, in certain cases. The other thing to think about is, what if here, instead of this boundary condition, we had a Neumann type? Suppose we said there's U prime, where the prime is with respect to the X. So let me do it as a partial. But we said partial with respect to X of U at the left end is 0, and partial with respect to X at U. What if this was the boundary condition instead? So that's what shows up on your homework 5. You have these types of boundary conditions. And so changing the boundary conditions, so in that case, I'd have a problem like this, where F prime equals 0. So changing the boundary conditions changes the nature of the problem, and therefore the nature of the solution. The point I'm trying to make is that when you look, the next time we look at a PDE, okay, the next time we look at the heat equation, okay, keep this in mind. The next time we look at the heat equation, the actual heat equation will be the same. The initial condition will be the same. That is, it'll be U of X at time equal to 0 is equal to some function. But the next time we look at the heat equation, the only thing that'll be different will be the boundary condition. For example, we might have insulated boundaries on both ends, like I mentioned, so partial U, partial X equals 0 on both ends, or maybe one side is insulated but not the other. But the point here is that, the next time we look at a heat equation problem, the only part we're going to change is this boundary condition, but that's going to cause the solution to look completely different. So that's really the thing I'm trying to emphasize to you, to be sensitive to how the solution is going to turn out, and what would happen to the solution if you change the boundary condition. Okay, so that's kind of the game when you work in PDEs, when you do research in PDEs. Typically, you focus in on one particular model. Like I work with Laplace equals 0. And then it's really about messing around with the boundary conditions. I don't know why I circled that randomly. Then it's really about what happens with the boundary conditions. That's why integration by parts is so important, because we can use integration by parts to relate what's happening inside the domain to what's happening on the boundaries. So now we want to solve this differential equation. Okay, so the tried and true technique is to let f of x equal e to the rx, where r is a constant. And so we get this so-called characteristic polynomial. And as I've mentioned to you a couple of times now, and I think this review is important. We'll look at this in 3 different cases. We'll check the case when lambda is less than 0. We'll look at the case when lambda equals 0. And we'll look at the case when lambda is greater than 0. Now, again, it's all about the boundary conditions. So here, for example, let me talk about, I briefly talked about the case lambda equal to 0 last time. Let me talk about this case. If lambda equals 0, go back to the original ODE. If lambda equals 0, then this entire left-hand side here, entire right-hand side here will equal 0. So this will equal 0 if lambda is 0. And so now I have the equation f double prime equals 0. I need another prime in there, hold on. F double, and now you integrate twice, right? First time you integrate, you get a constant, call it a. Second time you integrate, you get ax plus another constant. So here, I integrate twice, I get f of x equals ax plus b, okay? So now, if you apply the boundary conditions, I know, sorry, I can't help it. I'm obsessed with trying to write. So you get f of x is ax plus b in the case that lambda is equal to 0. Now, if you apply the boundary conditions, when x equals 0, you get b is 0. So let me make this a capital B. I wrote a little b because, like, from linear algebra, we always do ax equals little b. It's so funny. So yeah, so if x is 0, then b is 0. And if, so then f of x equals a times x. And then if f of L is 0, then a times capital L equals 0. And so you can cancel the L's and a is equal to 0. So you get a trivial solution. However, for example, in your homework on homework 5, if this was f prime equals 0, then in that case, you don't get a trivial solution for the lambda equal to 0 case. In that case, lambda equal to 0 is one of our eigenvectors, and I'll show you how that would affect things as we go later on. Okay, but anyway, back to this problem. In this case, with these, trivial Dirichlet boundary conditions, it ends up that if lambda is less than or equal to 0, we get a trivial solution. So the only case here, and this is a direct result of the boundary conditions, right? So I just want you to, appreciate that. Change the boundary conditions, we could change this scenario. So here we focus on the case lambda is strictly greater than 0. So if we let lambda equal to 0, we get these imaginary roots. And then we do some math trickery. Okay, so, I won't go to the details, but mainly if you look here, this is the solution. We have two solutions here, but then we use Euler's formula and rewrite it in terms of cosine and sine, and then take a linear combination of those solutions to come up with a real basis, real as in not complex, of the solution space. And so finally, also one of the goals here is to try to sort of use waves to solve these things, because these waves have many nice properties, the continuity, differentiability, et cetera, et cetera. So finally, we get this general form of the ODE as being, this linear combination of cosine squared lambda x plus sine squared lambda x. Now, pay attention here to how the, boundary conditions kick in again. At this point, the boundary condition kicks in, and we're actually able to eliminate one of the basis elements. But that's only because of this boundary condition. You change this boundary condition. If that was f prime of 0 equal to 0, things change. Okay, so I just want you to be aware of where the variation can happen in other problems, just to connect it up as we're working through this. So yeah, so here we see that this trivial boundary condition on the left end of the rod for the eigenvalue for the eigenvalue problem ends up getting rid of the cosine basis function as part of our general solution. And the trivial boundary condition on the other end of the rod, so f of L equal to 0. So here I just end up replacing this x right here with L, and then we set that equal to 0 and solve for it, and and you get that square root of lambda L has to be n pi. And so then we can solve for square root of lambda and find the eigenvalues. And so those are the eigenvalues. And so now it turns out so here's one of these subtleties that, well, there's more than one lambda, and for each lambda, we have a solution. And so, now we find ourselves in this strange position because this never happened with regular ODEs. We now have infinitely many solutions for the boundary value problem. And here, one subtle point, here n is plus or minus, I'm able to drop the negative because here sine of negative x equals negative sine of x. So sine of negative x is just a scalar multiple of sine of x. So in our basis, we want our basis to have only linearly independent vectors. So there's no point in having sine of negative x and sine of x, for example. So here, I just take the positive one. So it says I drop the minus signs. So now I have infinitely many solutions to the boundary value problem. But we want to solve the PDE, so we want to go back to the original, what we call product solution. Because remember, we said little u of xt was f times g. Now be careful here. When we started the problem, we just assumed little u. There wasn't a sub n here. We just assumed u is f times g. But because of what happened in the boundary value problem, it turns out we have infinitely many eigenvalues. Now, it turns out we have infinitely many product solutions. And what's with the g sub n? Well, so what's with this g sub n business? Well, remember, g is e to the minus lambda kt. So originally when we solved this time domain problem, right in here, we had g to the minus lambda here. So we had a lambda here originally. Then we solve the boundary value problem, and it turns out, well, it's not just one lambda, it's lambda sub n. And so this thing now we're calling g sub n.
Dr. Bott?
Yes, go ahead, Jacob.
For Fn of x equals C2, that C2 is the same for every single wave number.
It isn't. It's just a constant.
Right, but I'm saying it's the same constant. It's not. So we have a b sub n on the equation below. So that changes based on the wave number. The C2 is the same for every single wave number?
I don't know.
Okay.
I'm reluctant to say it is.
Okay.
Because it's kind of, the C is there because each solution itself, because of the homogeneity, any linear multiple of that solution will again be a solution. So this C, I think, can be any real number, and you'll again get a solution.
Okay.
Because this part's weird. Superposition applies whether I have more than one solution or not. So if you just had one solution, superposition would apply to that, and any linear multiple of that single solution would again be a solution because of the homogeneity and the vector space structure. If you look at the ODE for F, that also has a vector space structure. So I think this C2 can be any constant. I hope that makes sense. I hope that theory fits with you.
I think so. Thank you.
So now, so hold on, let me check one thing. So Brian asked, what exactly is lambda the eigenvalue of? Lambda, one problem with linear algebra is we think the eigenvalue problem is related to so lambda is the eigenvalue of this system of equations here. Here now, you should think of this not as lambda. Here, this should be lambda sub n. And now we have a system of ODEs. And we could conceivably, so that's more than one ODE. We have a bunch of them. So we could conceivably write that system of ODEs kind of in matrix notation. And that's where in linear algebra, the matrix eigenvalue problem comes from. But originally, like for an analyst, for someone who does PDEs, the eigenvalue problem, if you say it looks like this to a PDEs person, that's what an eigenvalue problem looks like. Yeah, so it's a great question, and it's complicated. So Sean asks, each product Fn times Gn is a solution. And yeah, they could each have a different coefficient front. So let me go back to that slide. So now we create the product solution here. And again, each one of these is a solution. Each single one superposition applies to, so any scalar multiple of each single one would be a solution, but superposition applies to all of them as well. So any linear combination of all of them would also have solutions. Yeah, so these B sub n's don't all have to be the same. And in fact, that's the only place we have any variation. Think about your Fourier series. The only place where we can have any difference between two Fourier series is in the coefficient values. The basis is always the same. So if I want to represent two different functions, it's really just about changing the coefficients. That's why people use Fourier series for, data compression. You just send the coefficients. You don't need to send the cosine sine part. That's always the same. I'll talk about that more in a second. So here now, using superposition, we stitch together all of the product solutions. Remember that we have accountably infinitely many product solutions, and any linear combination, that is any scalar times that, plus another scalar times the other one, blah, blah, blah. Any linear combination is again a solution. So now here's the giant, mega solution, right? Here's the giant mega solution that's got, that's the beauty of the vector space theory. That's why we're, so obsessed with the vector space theory, because this is one theory that allows us to take multiple solutions and stitch them all together. Here, the only part now where we have a room for variation is B sub n. So here, this would be a generic solution. So think about this. This solution that we have here is going to always be the form of the solution for heat equation where the boundary conditions are trivial Dirichlet boundary conditions. The solution has to always look like this, because up until now, that's the only information we've used. And now the only thing we don't know is B sub n, and the only piece of information we have not used is the initial condition. But up until this point, for every PDE where it's the heat equation and where the boundary conditions are this trivial Dirichlet, this is what the solution has to look like. The only difference now will be, what's your coefficient B sub n, and that will be determined by the initial condition. So that's would be the only place you could really vary the solution of two different heat equations with Dirichlet boundary conditions is in the initial condition. So you remember the Fourier basis, which is made up of sine n pi x over L, cosine n pi x over L, and the constant 1. That infinite basis is an orthogonal basis. But think about it. Any subset of the orthogonal basis will again still be orthogonal. It doesn't lose its orthogonality. And remember, when we say orthogonal, when you multiply two of them and integrate, it'll be 0 if the functions are different, and it won't be 0 if the functions are the same. So if I have an infinite basis, like the Fourier basis that we started with at the beginning, 1 cosine n pi xl and sine n pi xl, any infinite subset will still be an orthogonal basis. So here, if we just look at the signs by themselves, then we'll get what's called an orthogonal basis of signs. And here, when we apply the initial condition, we don't get a regular Fourier series because there's so many moving parts to this. For the Fourier series we studied were defined on minus L to L. In this problem, we're not on minus L to L. So be careful. In this problem, we're on 0 to L. And so, now there's so many questions I have to answer for you. So why did we study the problem on minus L to L? Because when we look at the heat equation on a ring, then we're going to have a domain that goes from minus L all the way to L when we look at the heat equation on a ring, okay, which we'll do next week. And the solution of the heat equation on the ring is kind of the most general version of a Fourier series. And I'll show you a little bit in a little bit that you can get the Fourier sine series and a regular Fourier series are actually related. The Fourier sine series is actually a special type of Fourier series. So just be patient. I'll explain it all here in a couple of slides, okay? But so yeah, you know, because of the boundary conditions, we ended up getting a basis involving only the sine function. And this is because of the boundary conditions. Because of the boundary conditions, I end up with a basis involving only the sine functions, and that's no problem because they're orthogonal. So using orthogonality, we can solve for b sub n. And I want you to be careful here. This formula is not exactly the same because we're not integrating from negative L to L. Okay? You know, how do you find the formula? It's just the usual orthogonality. Multiply both sides by sine of m pi x over L. And then integrate, I need a pi in there, over L. And then integrate both sides. I need to write this on both sides, but I'm not going to try and write it again. And then integrate both sides from 0 to L. That's supposed to be an integral. Then integrate both sides from 0 to L. Because of the orthogonality, anytime n and m are different, it'll be 0. And anytime n and m are the same, it'll be L over 2. So on the left-hand side, you'll just get, you know, b sub m times L over 2. And on the other side, you have integral 0 to L f of x times sine mx pi, and then you divide. And so that's where this formula is coming from. So you've done this a bunch of times. It's from the orthogonality. Okay, but just be careful. The domain here is 0 to L. So we kind of, you know, it's kind of a nice little review, actually, of our Fourier series in a slightly different environment. So here is what we call the formal solution. So this is the solution that's been mathematically created to be a solution. I don't know if it actually is. I don't know if it converges, and I haven't actually verified that it satisfies the original boundary value problem. So this is called the formal solution. So here's finally, this is basically the answer to every heat equation where you have trivial Dirichlet boundary conditions and the initial temperature is given by the function f of x. This would be the answer to, you know, our formal solution using separation of variables. And what you should notice, you know, really think about what you're looking at. This entire term is a constant. This whole thing, don't be fooled, right? This whole thing is a constant. The only place we have variables, we have an x variable right here and a t variable. Those variables match the x and the t here. That's the only place we have variables. This mess here, you know, as you remember, this is our b sub n. And, you know, you think about one component is kind of taking care of what's happening with the spatial dynamic, and one component is taking care of what's happening with the time dynamic. Remember here, we're trying to describe the temperature as a function of space and time. You know, so now to try and bring in the physical interpretation, you know, other thing that's really nice is to notice that we have this nice decaying term. And here for this problem with, you know, here we know the steady state solution is 0. We expect this entire thing to decay to 0 as t goes to infinity. And you notice the exponential part has that nice property. So I still need to verify the solution. And I'll do that in the next set of slides. And here, let me talk about what an odd extension, what the Fourier sine series is. Okay, so first I introduce some new notation. Oh, so let me mention one thing, and then I'll talk about the Fourier sine series. So here, for example, if I had different boundary conditions, and if we had an eigenvalue, if lambda sub 0 was an eigenvalue, if I had an eigenvalue at n equal to 0, then here the only difference with this sum would start at 0. And maybe I'd even write that 0th term out in front. you know, like we do with a Fourier series. That's the only place it would change. And if you change your boundary condition, it might change which basis element survives. Okay, so those are the only differences we would expect. And these remarks are, you know, relevant to the homework problem. I think problem number 2 in homework. Okay, so first, here's some new notation for a Fourier sine series of a function. Okay, so FSS. So here, please be careful. The function f of x in this case is only defined on 0 to L. Okay, so be really careful. This is different from what we did before. So we define this thing called an odd extension. So remember, if you know sine is an odd function, so the Fourier sine series is sum of a bunch of sine functions, that's going to be an odd function. So whatever it represents probably has to be odd. So we define this concept called an odd extension. So let's just think about this geometrically. So look, suppose I have a graph. So suppose the graph of f of x looks like this. So here, suppose the graph of f, I'm just going to, you know, so here's L. I'm just going to make up, you know, some graph. Suppose the graph looks like this. So that's f of x. So then when we replace x with a negative x, that flips it around here. And then you multiply by a minus sign, it flips it around the x-axis, and you get a function that looks like this. And so what happens is you get a function that's odd. So now if you look at this function that we ended up with here, that's an odd function. Okay, so this is called the odd extension of f. He just takes f, which is defined on 0 to L, flips it about the y-axis, and then flips it about the x-axis. I'll show you a picture in a second. So now here, so here's the theory. If we have f of x equals this Fourier sine series, again, the convergence theory is all the same as before. You need to be piecewise smooth to get pointwise convergence. Here, if f of x can be written as a Fourier sine series, where x is between 0 and L, okay, so that's really important. Then what the right-hand side, so here this right-hand side, you should notice, just like with a regular Fourier series, this thing is continuous, it's periodic, and in this case, it's also odd. So how do we interpret what the Fourier series, this Fourier sine series, did to the function? So we interpret it as being the periodic extension of the adjusted odd extension of f. So yeah, you should think about all those words. Here's all the notation. So first, we start with the original function f, which is defined on 0 to L. Then we make it an odd function on minus L to L. So that when we do the extension, now we have a function on minus L to L. Then we adjust it. That is, we fill in any removable discontinuities, or where it has a jump discontinuity, we define it to be at the average, and then we periodically extend it. And so we can think of the Fourier sine series of f, which is defined on 0 to L, to be just a regular Fourier series of this odd extension of f, which is defined on minus L to L. So this is a good review of your Fourier series theory. Here's a picture. So I started with x. So I want to know what's the Fourier sine series of this function x defined on 0 to L. Well, first I do the odd extension reflected about the x-axis, so the y-axis, and then the x-axis, you know, or whatever order. So then you get, it looks like this, and then you lift it, you get that. And then adjust it, right? So periodically extend it and adjust it. So here you can see I've averaged it at its jump discontinuities, and the removable discontinuity here has been taken out. That's the adjusting, and then you have your periodic extension. So that's what the Fourier sine series of f of x, where x is defined between 0 and L, would look like. It's also just the regular Fourier series of, you know, the odd extension of x on minus L to L. Okay, so this is part 2. I just want to talk about the procedure where, what if we don't have a steady state solution that's trivial? How do you decompose it? And make some comments about convergence. Okay, so here convergence, we're really lucky because of that decaying exponential term, we'll get nice convergence behavior. So this is just a review of what we talked about before, and so I won't get into this, but you should definitely review this a couple of times. So for the method of solution, so let me stop. Sorry, this is the wrong file. I need to open the one with the transitions, my bad. Wah, wah. Try again. Mondays strikes again. So yeah, here we go. Part 2, there we go. Okay, my apologies, everybody. Let's try that again. Okay, there we go. Shit. All right, so let me talk about part 2 of solving the heat equation. This slide is just reviewing what we talked about last time, so please take a look. So in general now, what's our strategy? Okay, so I want you to think now big picture. So given a partial differential equation, a PDE, and some boundary conditions and an initial condition, if we have the following 3, situations here. If number 1, the set of functions that satisfy the PDE and boundary condition form a vector space. Right, I didn't include the initial condition. 2, if there's a non-trivial function v of xt that satisfies the PDE and boundary condition, which is called a transient solution. And 3, if the PDE has a steady state solution, call it u bar of x, then the sum of the 2, u bar plus v, will be a bona fide, will be a solution to the PDE. So then when you add the 2, this will be a solution that satisfies everything. It's been reverse engineered, I'll show you, to satisfy everything. That's assuming, in our particular case, we get a solution that's in the form of a series. So we have this additional requirement of worrying that does the series converge? But in general, if you have the steady state solution and a transient solution, then you can cobble together a solution to the PDE. Evan, did you raise your hand?
Yeah, I had a question. So it says the set of functions that satisfy the PDE and the boundary conditions form a vector space. Is that the homogeneous boundary conditions, or is that any boundary condition?
In theory, any boundary condition.
Okay.
But they would have to be equal to 0 because that's the only way the closure would work.
Okay.
So they could be Dirichlet or they could be Neumann, but homogeneous, or one side's insulated, one side's not insulated. But I would think they'd have to be homogeneous. I don't get how you get the closure without it equaling 0. So yeah, I would agree with your kind of overarching point there. So as we talked about this, that the steady state solution kind of takes care of the long-term behavior, and the transient solution takes care of the short-term behavior, takes the time part. So to our heat equation with the homogeneous Dirichlet boundary conditions, we can integrate twice. Like I said, you can, if I assume partial u partial t is 0, because I want to find the steady state. So assume partial u partial t is 0. So this side of the heat equation is 0. Integrate twice, I get this, ax plus b or whatever, c1x plus c2 as our solution. But then when you apply the trivial boundary conditions, it zeroes everything out. Okay. So in this case, our solution actually looks like 0, the transient solution, plus v of xt. V of xt is the thing we found before using separation of variables. Instead of doing separation of variables to this function, v of xt, I just did it directly to u of xt, but you see they're equal, u equals v. So in general, suppose we have non-trivial boundary conditions, non-trivial Dirichlet boundary conditions, then what do we do? Okay, so let me show you what we do when we have so-called steady conditions. So here I've got Dirichlet but not homogeneous. So this is some fixed constant T1, assume it's non-zero, some fixed constant T2, assume it's non-zero. Everything else is the same. The only place we've changed something here is in the boundary condition. So now here, the set of functions that satisfy the PDE and boundary conditions do not form a vector space. And you should think about why that is. The problem is right here. The problem is with these. If they're not homogeneous, if you have two functions that satisfy the boundary condition, when you add them, then the sum will equal 2T1, which is not equal to T1. You know, that's the beauty of zero. 0 plus 0 equals 0, you know. So here, in this case, I'm going to make this assumption that U equals U bar plus V. And now we're going to take this assumption and plug it in to the PDE, to both sides of the PDE. And so I'm going to plug it in here to the left side and to the right side. And then we're going to equate the like parts. So for partial U, partial T, when I plug in U bar plus V, U bar isn't a function of T. The derivative of U bar with respect to T is just 0. So that's what this 0 is coming from. And then partial of V with respect to T is partial V, partial T. And now on the other side, let me plug in U bar plus V into this second partial with respect to X over here. And so again, you know, you take the derivatives of each part, the derivative of U bar with respect to X, the second derivative with respect to U bar is K U bar double prime of X. And the second derivative of V with respect to X times K is K second partial of V with respect to X. So look, here's the left-hand side of the equation, okay? Right here. And here's the right-hand side of the equation. So we've got this is equal to this. And they're supposed to be equal to each other. Right, so now these two are supposed to be equal to each other. So here's where the math trickery happens. There's a lot of options here, but we're going to break this up in a very sneaky way. Okay, so watch. I'm going to set basically what, you know, I call it the like parts equal to each other. So I'm going to set partial V partial T equal to K second partial of V second partial of X. That's really natural. They both involve the V variable. They both involve partials. And then I'm going to set the other parts equal to each other. So here I'm going to set what's left over, KU double prime, equal to whatever's left over. I'm going to set that equal to 0. And so you see that gives us the steady state equation. And then we have the equations for the transient solution. So here's my steady state. And then here's the transient. And you connect up the parts here. So this is the left-hand side right here. And this is coming from over here. And this is, you know, I divided both sides by K. So now I just need two things. So be careful. This is not a complete boundary value problem. I need boundary conditions and I need an initial condition for V, not for U, for V. But it's very easy now. We just use this over and over again. Use this assumption over and over again. Because here to find the boundary condition now, replace X with 0. So wherever there's an X, I'm going to replace that with 0. set the whole thing equal to T1. So that's what I've done here. T1 equals U0 of t. That's the boundary condition for the original PDE, but I'm assuming U of xt equals U bar of x plus V xt, where x is replaced by 0. So now just solve for V. Oh, so here, be careful, sorry, not solve for V. So here, what we want to do is we want V to have trivial boundary conditions so that, you know, it'll have a vector space structure. So put the non-homogeneous boundary condition on the steady state. Let U bar of 0 equal T1 and put the non-homogeneous part on V sub 0. So let V sub 0 just equal 0. So this becomes the boundary condition for the transient PDE. Similarly, do the same thing at the other end. So here I say T2 equals UL of t. That's the boundary condition for the PDE in U, the original variable, but U equals U bar plus V. I've replaced the X with capital L. Again, I want the PDE to have homogeneous boundary conditions, just like Evan said, so that we have vector space structure. So let U bar of L equal T2 and let V equal the trivial boundary condition 0. What's important is if you add these two, you get T2, that we still satisfy the original equation. Finally, for the initial condition, use this equation again. And here now I'm going to plug in 0 for T on both sides. And we know the left-hand side will equal f of x. So here, f of x we know is the initial condition is equal to u of x0. That's the initial condition for u. U of x0 equals u bar of x plus v of x0. So now just so u bar doesn't have an initial condition. U bar is time independent. So here we need to solve for v of x0, find an initial condition for v. And so now these three equations now, if you look at these three, here's the PDE, here's one boundary condition, here's another boundary condition, here's our initial condition. That solves the PDE for our transient problem. And then I would now use separation of variables on this. Now do separation of variables to solve this problem. And then once we find the solution V, and once we find the solution U bar, then we add the two to find the full solution. So here, let me just end with this next slide here. So here I put, here's the steady state solution, which I also solved, and then here's the transient solution. And we know from the previous slide, the solution to the transient solution is this. The only difference is before our initial condition was fx. Now our initial condition is f of x minus u bar. So that's what's changed right in here. That's the only difference from what we did before when we did separation of variables. And so now we're going to add the steady state solution and the transient solution. So you get a solution that looks, there's the steady state part plus the whole transient part. And, you know, be careful here. The only variables are right here. X right here is a variable, t right here is a variable, and x right here. Those are the only variables. Everything else is a constant. All right, folks, so take a look at these slides. This is kind of the more general approach. When the PDE and boundary condition do not form a vector space, we decompose it so that the transient part does. You can see. And then we add the two together, the steady state and the transient solution at the end to find the answer. So take a look at these next two slides. So the next slide I'll talk about next time talks about convergence, and that's fairly quick. The convergence is really nice because of the exponentially decaying term. All right, everybody. So I'm going to stop here, and yeah, I'm just going to stop here, and I just want to thank you for your time and have a great day.